Morning class, we are looking at 1.4 exponential functions. So we covered a bunch of sections. Reminding you of exponential and logarithmic functions that were discussed previously, okay, and their properties. As long as we know the definition, y equals log x base a means x equals a to the power of y, pretty much we can handle just about everything. So it's extremely important to be comfortable with the definition. Then we looked at the new functions from the old functions. We looked at algebra functions. We looked at their the composite functions, and we looked at the their intervals domains, which was simply put the intersection of their domains in the case of each and every one of them. In the case of the quotient function, the denominator, remember, can never be zero. For the composite functions, if you're looking at f of g, whatever is in the domain of g that has to be excluded must be excluded from f of g, and then we look at the result of f of g and make further decision about that. So we're going to start the new stuff, and so let me stop the video to make it a little bit, sharper when we do the report. So let's take it from here. We put it in slide show. They are covered. The first thing I want to remind you is the definition that results in the following formulas that we have seen. When we looked at exponential functions, the very first thing we need to know that is helpful here are exponential rules. The zero exponential rule, a to the power of 0 is 1, the product rule, the quotient rule, the power rule, the negative exponential rule. Everything that you see on the left side, those are rules you've seen. There's nothing brand new there, okay? Now, when we look at an exponential function, okay, y equals b to the power of x, depends on the value of b. If b is between 0 and 1, looks like the left side, okay? And if it's larger than 1, looks like the right side. And if you choose b to be 1, it is not an exponential function. It is not an exponential function. Okay. So when a is larger than 1, we are looking at an increasing function. We also have the limit of f of x as x approaches infinity is infinity. In other words, notice what happens. We are really looking at the concept known as the end behavior. The end behavior was discussed in college algebra and pre-calculus. So you're looking at the end behavior of a function. Okay. When by a we mean the base. Okay, so this one over here probably we mean b. Either way is fine. And so it really pertains to this one. On the other hand, if you're looking at the case where the base is between 0 and 1, the function is decreasing, therefore the limit of f of x as x approaches infinity becomes 0, which means is the precise definition of the horizontal asymptote. So you are looking at the end behavior. On the other hand, if the x is approaching negative infinity, f of x blows up to infinity. What else is interesting about this function is that in general, there is no vertical asymptote. The y-intercept happens at 0, 1. There is no x-intercept. The domain is all real numbers, and range is from 0 to infinity. Okay, class. So it's important to distinguish between the two and being able to uh, detect all of the information that I told you from the graph. It's really simple. As long as you have the graph, pretty much you're done. Okay, so when we look at essential functions, basic functions, remember the graph. If you have the graph in your mind, you're practically done. So I hope you learn them in this fashion. Okay, graph of the function tells you everything you need to know, just for the sake of argument. If you look at this function, this is the graph of, roughly, this is obviously
So logarithmic functions
not precise.
Transformations are expected to be smaller. It's not to scale. It's not important as far as happens in order for the positive.
Okay. If you're looking at this function, you're looking at the graph. So the graph tells you everything. For example, it gives you the limit of the function, if we call it f of x, y, or f of x, as x approaches infinity. What does that mean? If we are going this way, what happens to the y? The y goes to infinity also. So the graph gives you just about everything you want. The domain, for example, is all real numbers, so on and so forth. So I hope you realize the importance of remembering the basic graph that can tell us everything we need to know. All right, so going back to what we were looking at here. An exponential function, you need to know the graph, okay, class? You need to know the graph so you can easily answer everything that comes up. All right, so with that being the case, just the basic graph of f of x equals 2 to the power of x, you know the general idea. When the base is larger than 1, how it looks like. Of course, we can plug in, but I'm really interested in the general shape of a basic graph. So remember, when f of x is a to the power of x, or b to the power of x, whatever the base you want to call it. If the base is larger than 1, this is the shape. Now, basically, when we start the graph in the beginning, and that's what we did in algebra, when we started the graph, we had no idea about it. We just did, plotted points. So if you pick enough points, you can see the graph. Now, what you notice, of course, there is no x-intercept. The y-intercept is at 0, 1. Domain is all real numbers. Range is from 0 to infinity. And we have a horizontal asymptote, which is the x-axis of y equals 0. This is an increasing function, all of the above, okay? For f of x or 3 to the power of x, you do the same thing. Now, ultimately, the shape is very similar. The only difference is, because the base is larger, what happens to the graph? The graph gets closer and closer to the y-axis, class. So you can pick up various points, a bunch of pairs, and you see the graph. So 2 to the power of x, 3 to the power of x, okay, or 5 to the power of x, or 10 to the power of x, or e to the power of x. Ultimately, they look pretty much the same. They look similar, okay, class? And what you see here, it works for all of them. The intercepts, the domain and range, the asymptotes. There is no vertical asymptote. There is a horizontal asymptote. This thing works for any function, okay, of the form y equals a to the power of x, where a is larger than 1. So everything that you see here, and this is the generation. I hope you see the concept and you stick with that. All right. Again, I'm refreshing your memory about what we learned about, exponential functions before. Now, 1/2 to the power of x. We do the same thing. In the beginning, we just pick up a bunch of pairs. Let's do that. I'm hoping we have no problem by plugging in. So we get a bunch of pairs. And if we graph it carefully, the function y equals 1/2 to the power of x looks something like that. Now, if we change y equals 1/2 to the power of x to any number, okay, as long as the number is between 0 and 1, it has the same shape. And therefore, we are going to repeat everything that we wrote in the previous page. X-intercept none, y-intercept is still 0, 1. See that? Okay, domain is still the same thing, all real numbers. Range is the same thing from 0 to infinity. Horizontal asymptote is the x-axis. The only difference is previously we were dealing with the increasing function. Now we're dealing with the decreasing function. And this shape works for any function of the form. Let me see if I can pick a different color now. So if y or f of x equals a to the power of x, where a is between 0 and 1, the shape is what you see. The only difference is as a, the base gets smaller, it gets closer to the y-axis. Just for the sake of argument, if I were to look at this graph, right, and let me use a different color now because screen. So if I graph something like that, this would be something, for example, smaller, the base is smaller than 1/2, maybe 1/3 to the power of x. That's the idea. Now, the smaller the base, the closer to the y-axis. Again, to refresh your memory as far as what we learned in pre-calculus. So remember the shape of every essential function, just to be on the safe side. All right. The graph of 3 minus 2 to the power of x, we want to graph, we want to sketch the graph, and we want to come up with the domain, range, everything. So obviously for a case like this, we are expected to do it by some basic transformation we've learned, and it starts with the basic function y equals 2 to the power of x. So you have y equals 2 to the power of x, you know the shape. It doesn't have to be perfect, okay? If it's not to scale, so be it, a rough sketch. But what are the transformations we need to use, okay? So the next one is to do y equal, y, let's say this is y sub 1, then y sub 2 equals negative 2 to the power of x, okay? Which is the reflection about the x-axis, okay? So we simply flip it over. And there's only one more step left, and that is to move it up by 3 units. Move it up by 3 units, class. We are going to bring it up, shift it up, however you want to put that, by 3 units. So it's important to see, for example, what happens to our y-intercept and how it shifts. Okay, class? This is important. It's very straightforward. I hope everybody's comfortable with that. Now, what do we notice? Okay. We notice the new location of the y-intercept. We notice the domain hasn't changed, it is still all real numbers. We notice the asymptote, horizontal asymptote, which used to be x-axis. Now it's y equals 3, okay? And therefore the range that was from 0 to infinity has changed from negative infinity to 3. Okay. I hope everybody is clear on this. So I want to add horizontal asymptote clearly located at y equals 3. Everybody can see that. Okay. Horizontal asymptote at x equals 3. So that's very straightforward. We should have no problem with that. Horizontal asymptote. All right. So it was a simple, transformation, and hopefully we are all comfortable with this and we remember the basics as before. Okay, that's explained in the previous section as far as the transformation, refreshing your memory. Okay. All right, class. Now, what happens when we deal with the exponential function f of x equals e to the power of x? As you recall, e is just like pi is an irrational number. It's an important number. E is roughly about 2.718, but really it's a irrational number, 2.71828 continues indefinitely. And so the graph of e to the power of x and 2 to the power of x and 5 to the power of x and 10 to the power of x ultimately look the same. And that's the idea that I want you to pay attention to. So when we look at the bottom graph, okay, look at various bases, okay? The bases are larger than 1 versus the bases that are between 0 and 1. Larger than 1 means increasing, okay? And so if you compare 2 to the power of x and 3 to the power of x, and that's what we do in calculus, by the way, we notice something about, and that's the importance of the natural exponential function. That when we do the tangent, and we discuss the tangent line with more details, I guess everybody has some idea. Later on, when we delve into more of calculus. At its x-intercept, for one of them, the slope is 0.7, for one of them is 1.1, and for exponential functions, natural exponential functions, that slope is equal to 1, okay? So that's one of the importance of this function. Now, as far as the definition, one of these definitions has, we've done it in algebra, and one of them requires calculus for the proof. We are going to revisit this, and I'm going to go over the proof of these definitions. E is equal to the limit of 1 plus 1 over n to the power of n as n approaches infinity, or E is the limit of 1 plus h to the power of 1 over h as h approaches 0, or the limit of e to the power of h minus 1 over h as h approaches 0 equals 1. This part was seen in algebra, and this is in calculus. So algebra, and this is in calculus. Okay. We will look at it with details later. Okay, class, we will go over the proof of that because we haven't really discussed the limits yet. All right, we want to graph this, and again, the idea is that start with a basic function. In this case, the basic function is e to the power of x, and we know how the graph looks like. Again, looks almost like 2 to the power of x, 3 to the power of x, roughly, you know. Okay. So now what we are going to do, we are going to go to e to the power of negative x. When x changes to negative x, you have a reflection by the y-axis. So we go with e to the power of negative x. And this is the new graph. Okay, so we started with e to the power of x, then e to the power of negative x. Okay. And now we are going to move on with the next step. Now we see a number 1/2 in front of e to the power of minus x. So we're going to use that and multiply e to the power of minus x by it. So when we do that, okay, it compresses the graph and it shrinks the graph along the y-axis. So right now, the y-intercept is at 0, 1. Now it becomes 0, 1/2. So we use 1/2 in front of e to the power minus x. And the result is that the graph compresses, and again, look at this y-intercept, both of them located at 0, 1. And now it's 0, it's at 0, 1/2. And now minus 1, that means just take it down by 1 unit, okay? So we are going to bring it down by 1 unit. When we do that, the graph looks like this. So we shift the graph down by 1 unit, okay? And as a result, we end up with the domain which is the same as before, all real numbers. But the range changes from 0 to infinity to the new range of -1 to infinity, and giving us the horizontal asymptote, as you can see. The horizontal asymptote y equals -1. The horizontal asymptote of y equals -1. I can't really emphasize this enough, class. Okay. We have that. Let's look at some sort of algebraic, operations we have seen before. Starting with part A, we are interested in simplifying that. And I hope you see the easy way out for part A is simply using what? Exponential rules. Exponential rule says, okay, the rules for exponents. If you look at the top and ignore the bottom, all you have to do add up their exponents. So 2n and 3n minus 1, we can add them up, okay? And that results, when we add them up, that results in 5n minus 1. Now, the next step is to subtract n plus 2 from 5n minus 1. We are using the quotient rule. So 5n minus 1, subtract from it n plus 2, and this gives us the new exponent 4n minus 3. I hope it's a straightforward, class. Okay, there is really not much to it, very simple. So we are using the exponential rules. First we use the product rule, then we use the quotient rule. Product rule, quotient rule. Okay, class? Okay. In order to simplify B, we have to go to law of exponents. To do that, first we have to change them such that they look like exponents. To do that, from roots, we change them accordingly. Everybody knows that Square root of a is a to the power of 1/2. Cube root of a is a to the power of 1/3. And what I want you to, of course, remember, when the index is odd, we have no restrictions. When the index is even, what's underneath must be a positive. And remember, in this case, the limitation is a is positive. Okay, and that is the assumption. So now what happens is that this square root of b itself can be replaced with b to the power of 1/2. I hope you know that. So when a comes out, becomes a to the power of 1/2, but when b comes out is b to the power of 1/2 and then times 1/2, which is b to the power of 1/4. The other thing I want to add, it might be helpful, is the following. Just to, if we have this, that's the essence, okay? It's really the same as the 4th root of b, okay? Why is that? When we don't write the index class, remember the index when we don't write is 2. So if we happen to have, let's say, the 3rd root of the 4th root of a, you just multiply the indices. 3 times 4 is 12. So this is a property that hopefully you remember from algebra. So with that being the case, okay, we look at the numerator. So going back, okay, so a to the power of 1/2, b to the power of 1/4, and to the bottom is a to the power of 1/3, b to the power of 1/3. So for this part, we can say a to the power of 1/2 minus 1/3, and for this part, b to the power of 1/4 minus 1/3. And that's a simple case. Everybody can add up fractions. The first one is 1/6. The second one is negative 1/12. I hope everybody's comfortable with that, so we don't have to worry about that. Okay. All right. So that's just dealing with some expressions and simplifying them accordingly. We are given a function y equals e to the power of x, and we have the graph. It's a basic essential function everybody's familiar. And we want to know how it works out if we want to reflect it about the line y equals 4. The first thing you need to remember, y equals 4, okay, is a horizontal line. So this is a horizontal line, okay? And remember, the x-axis is a horizontal line. So that's the concept. You are really thinking about the x-axis, in this case, y equals 4. So the very first thing is that you can reflect it about the x-axis, because remember, y equals 4 is parallel to the x-axis. Okay, it's a horizontal line. And then because it's not y, remember, x-axis, I want to put this up here, x-axis, y equals u. That's important to remember. And so now it's 4 units away from that, and reflection makes it 2 times that. So the idea is that first reflected with respect to the x-axis. Just flip it over. And then because y equals 4, any number that y is equal to, multiplied by 2, okay, and shifted. In this case, 2 times 4 is positive 8, so shifted positive 8 units up, okay, because of the reflection. When we look at the second part, we want to do the same thing, but this time with respect to the line x equals 2. Remember, this is a vertical line. Let me use a different color class. This is a vertical line, okay? And remember, the y-axis okay, has the equation x equals 0. So x equals 0, vertical line x equals 2 is 2 units away from that. So first we do the reflection accordingly with respect to the y-axis. Okay, gives us this. And then we shift it by 4 units. Okay, 2 times 2 or 4. And that's what we get. Okay. Two times 2 equals 4. About the line x equals 2, you shift it by 2 times that because it's 2 units away. Remember, you are reflecting. Just think about the concept that happens as a result. We are going to look at more examples involving algebra. Okay. So for example, in part A, we are interested in finding the domain. And just to refresh your memory, when you're looking at y equals square root of x, domain is x, larger than or equal to 0, or basically from 0 to infinity. Okay. This is precisely the same as far as the concept. So going with that, the very first step is to put the radicand, it's called radicand, larger than or equal to 0, and solve this inequality. We move the 100, and we know 100 is equal to 10 squared. Everybody knows that. Okay. So 10 to the power of t larger than or equal to 10 squared. So t must be larger than or equal to 2 accordingly. And you can test it. If you choose 2, it's 0. So if you go back and put in 2, you get 0. And anything larger than that makes it positive. Okay. All right. Part B, in order to find the domain, we are looking at really a composite function in essence. You can think of g as sine x, if you will, sine of f of t, you can think of it, and f of t is e to the power of t minus 1. This is a composite function. So when you're looking at a composite function, you look at the shell, which is a sine. Remember, the domain for sine is all real numbers. The sinusoidal functions, they don't have any restrictions when it comes to their domain. So sine has a domain that is all real numbers. So this is all real numbers. And then inside, now you're going to look at the restriction on inside, because the inside might give you a restriction. But if you recall, exponential functions, e to the power of x, doesn't have any restriction. So the domain for the inside is also all real numbers. So the sign doesn't give you any restrictions. So you go with the restriction for the argument of sine. E to the power of t minus 1 is called the argument, okay? Argument of sine has no restriction. The domain, therefore, is all real numbers, okay? The domain is all real numbers. And again, one way to look at this, you can write g of t equals sine of, let's say, h of t, where h of t is e to the power of t minus 1. That's one way to look at it. And either way, you'll have the same answer. So we want to solve for t. Here's the question: e to the power of x squared times e to the power of 2x plus 1 equals e to the power of t. And this is a simple case class. All you have to do, simplify each side such that both of them have the same base e. The right side has base e, the left side can have base e by simply adding up. Remember, this is the product rule, okay? Which means a to the power of m times a to the power of n is a to the power of m plus n, okay? So we add them up. X squared plus 2x plus 1 is e to the power of t. And therefore t is the same as x squared plus 2x plus 1. And you're done. You simply use the product rule and it works out. Okay. So we are looking at some basic ideas from pre-calculus. We are going to move on to the next section, to the next question class. Okay. We want to find the exponential function such that f of x is c b to the power of x. All right. To do that, we can see the two pairs, and we write the two pairs, negative 1 comma 3, 1 comma 4/3. So basically, you have two equations, two unknowns, okay? What are your unknowns? The c is unknown, the b is unknown, but you have two pairs. So plug in and come up with the answer anyhow, and you're done. So I hope it makes sense to everybody as far as the concept is concerned, okay? And so with that being the case, if we use the first pair, f of x, remember, is y. This is the same as y. So 3 is cb to the power of negative 1. And everybody knows cb to the power of negative 1 means c over b. Okay? So that's not a big deal. And therefore c becomes 3b. Let's use the second pair, 1 comma 4/3. 1 comma 4/3. So 4/3 is c times b to the power of 1, cb. cb. Okay. So practically we're done. I want you to look at the very first equation, if you will. You can think of this as equation 1. And I want you to think of this as equation 2. 4/3 is equal to CB. And I hope you see the easy way to solve this is by substitution. So you know C is 3B. So replace the C with 3B. So you get 4/3 is 3B times B, which is 4/3 equal to 3B squared, right? If you divide by 3, you get B squared, and B is plus minus 2/3, and we just keep the 2/3. It is important to see right here, class, the answer becomes B is plus minus 2/3. There are two answers, okay? But remember, the exponentials, the restriction is B is positive, okay? And so if you have B, C is 3 times that. B is 2/3, C is 3 times B, And now your function f of x is cb to the power of x, cb to the power cb to the power of x, and you plug it in, you have the answer. So I hope it's straightforward as how we arrive. Okay.
Professor,
Yes.
a quick question. How did you get c is equal to 3b again?
Okay, let's go back to make sure everybody is following that. You want to, let's see where I want to, which, you're talking about this step?
Yeah, like right
C
there.
equals 3b, this step,
Yeah.
right? Okay.
Right here, yes.
Okay. You're okay with the very first step where we plugged in, right?
Yes.
Okay. cb to the power of -1. When we say cb to the power of -1, that means c times 1 over b. That means c over b. Okay. So this means c over b. And then 3 equals c over b, you do the cross product. I want you to look at this one. 3 equals c over b, right? This is correct? You okay with this one?
Yeah.
Now you do the cross product.
Okay. But don't we have to, isn't it 1 over 3, not 3 over 1, if we bring down the b?
No.
Okay.
It's c, okay, it's very simple. You see this b here? You can multiply both sides by b. So
Yeah.
I want you to ignore that and look at this equation. What do you have? 3 equals c over b. Am I right?
Yes.
Okay. Now multiply both sides by b.
Okay.
Yeah. Maybe if I wrote that as from here, if I wrote it as 3b equals c, maybe it makes it easier to follow.
Yeah, it makes it easier like that.
Perfect.
Thank you.
My pleasure. Is everything else okay? Every other step is okay?
Yeah, everything makes sense.
Perfect.
Thank you, Professor.
My pleasure, Zain. Okay. So the process is we have a nonlinear system of equations. Okay. Let me see if this can be helpful. If I can show something here. Okay, so we have let's show you something that might be helpful. We have this one. There we go here. Okay. And we have here, this is a question. I hope that will be more helpful if I put it here. Okay. So here's what we have. What I want you to see is really the following. We have the following system of equations. Okay. This pair, so maybe I do it like this. We have the pair -1, 3, and we have the pair 1, 4/3. Okay, and we have this, right? So I'm going to rewrite this here, okay, as y equals cb to the power of x, okay, or cb to the power of x equals y. Maybe even that one is better. So we have this, and we are going to put the very first pair in it, okay? So c is missing, b is missing, x is -1, y is 3. Look at the next one. C is missing, B is missing, X is 1, and the answer is 4/3. So what I want you to see is this. You are solving this system of equations. It's called a nonlinear system of equations. Is everybody following that? I hope this is helpful. Okay, so this ends up being C over B, and this ends up being CB. You can solve B or for B or for C. In one of them, put it in another one. You have the system solved. So this is the idea. You're dealing with a system of equations, but it's a nonlinear system of equations. So I hope that was helpful. So again, you have two pairs and you put them into the function f of x equals cb to the power of x. You go through the process, solve, and you're done. Okay. All right. Here's a question. We are looking at more of the questions involved in this concept. A bacteria culture starts with 500 bacteria and doubles in size every half hour. How many do we have in 3 hours? How many are there after 3 hours? And how many are after 40 minutes? So what I want to do, class, I want to approach this two different ways. First, I want to approach it just very basic, even basic algebra, and then I want to look at it from the point of view of the formulas we've seen in the past. That does involve exponentials and, of course, logs to a certain degree. Now, if we want to go with the basic concept, okay, and you have 500 to begin with, and it doubles in size in 30 minutes. So 30 minutes later, you have 1,000, okay? Another 30 minutes, you have 2,000 and so forth. So you want to see the 3 hours corresponds to how many 30 minutes in essence, okay? If you want to look at it from that point of view. So 3 hours, if you divide by half an hour, gives you 6 of those doubling periods. And that's why it's 500, the initial, times 2 to the power of 6, or 32,000. You can do it one by one. I did a couple of them for you. So you have 500 in 30 minutes. In half an hour, you have 1,000. In 1 hour, which means 2 of those half an hours, 1,000 doubles up to 2,000. Another 30 minutes, 2,000 goes to 4,000, so on and so forth. This is a basic approach, okay? However, I'm really more interested in solving B and then the general format. So the B says, if you recall, y of t is y sub 0 e to the power of kt. We're looking at the exponential growth, okay? Where y of t is the size at any given time, y sub 0 is the initial value, okay, and k is the rate of growth, which means now with the doubling time, okay, now y sub 0 becomes 2 times y sub 0. In other words, I don't even need to have 500. I just know that in 30 minutes, which means 1/2 of an hour. So I'm going to replace the left side with 2 times y sub 0, and the right side, y sub 0 e to the power of k times the t. T is half an hour, 0.5. So I hope everybody can see what I'm doing. Now I'm going to drop the y sub 0 because I can divide it. Now, if instead of y sub 0, remember this is y sub 0. If you put 500, it makes no difference. Whatever it might be, it goes away. So you simply have 2 equals the right side. Now, how do you find k? You take a natural log of both sides. ln of the left equals ln of the right, and ln of the left is ln of 2, but ln of the right becomes k times 0.5 or 0.5k. So what is k equal to? Okay, k equals ln 2 divided by 0.5. Division by 0.5 means multiplication by 2. So k equals 2 times ln 2. Now, granted class, you can use a calculator and ln2 gives you an answer which is an irrational number, but you have to write tons of decimals to be on the safe side. But if you kept it as 2 ln2, that's fine. And you can say y of t is 500 e to the power of, now 2 ln2, okay, again, ln2 is just a irrational number, you can find it, okay? But keep it as 2 times ln2t to be, to have a precise answer, okay? And so if we go this route, take a look at what happens to part A. We want y of 3, which is 500 e to the power of 2 ln2 to the power of 3. And I hope you can see that this part is the same as 2 to the power of 6. Why is that? I hope you remember that. E to the power of ln x equals x. So e to the power of 2 ln2 e to the power of 2 ln2, I'm going to put ln2 and then 2 and 3 together as 6. This is, sometimes it acts up this stylus, okay? And this is 2 to the power of 6. Okay, that's how you arrive at it. This is a basic algebra, okay, class. I hope you're comfortable with that. And you get to the same answer, okay? If I were to approach B differently, okay, at least, again, the basic idea without knowing the exponential format that was discussed, you can say 1 hour is 2 doubling period, t hours is 2t doubling period, and you can say y is 500 times 2 to the power of 2t, and that works. And for part C, now you have two choices. 40 minutes is 40 divided by 60 hours. 40 divided, so 40 minutes. 40 divided by 60, or 2/3, okay? And so you can put that into any of these equations. So you can use this equation, or you can use this equation, either one, and put t equals 2/3. I highly recommend, I did one of them. I highly recommend you do the other one and come up with the answer. By the way, we are looking at the number of bacteria. So you just write the answer and do the, approximation by changing it to a whole number accordingly. That's extremely important. Okay, class? Now, the synopsis of the rules that you are supposed to know, and it will help us go to the next section, is the following, okay? For 1.5, inverse functions and logs. As long as we know this definition, that when we're looking at a log, it simply put gives us the concept of an exponent, okay? And if we really understand that, we have no problem with the rules. So here's the basic rules you are supposed to know, and many of them come with from a simple definition of a log. Just as an example, b to the power of 0 is one. To look at this arrow that I use here, class. Okay, if you put the y on the other side, okay, if I put the y on the other side, this arrow tells us what? B to the power of y is x. Okay, so that might be helpful in this. So this arrow. B to the power of y is x. Remember that, and that will help you. Now, these two together refer to the fact that logarithmic functions and exponential functions are inverse functions, class. I highly recommend you get comfortable with those. Okay. The next one is the product rule. Log xy base b is log xb plus log y base b. Log of x over y base b is log of x base b minus log of y base b. And log x to the power of n base b is n log x base b. That is the power rule. Okay. When we look at common log, the base changes to 10. We do not bother to write that. It's important to see that we don't write the base. Okay, class? That means common log. Now, in the case of a natural log, we use ln. We use ln. Okay? Now, take a look at the transition. If you could look at the left side and those rules, logarithmic rules, and you make up these rules, they should be nice and easy. You are in good shape. If you can't make them, you have problem with logarithmic, properties. Okay, just for the sake of argument, the first one, log 1 base b, we just write ln 1. We don't write the base b. Now, look at the second one, log b base b. That means the argument of log and the base must be the same. When we write ln, we know the base is e, so we write the argument as e, ln e equals 1. Okay? And the other two, as I mentioned before, refer to the fact, and I went over this in the previous page, when I wrote e to the power of ln x equals x. These two properties refer to the fact that exponential functions and logarithmic functions are inverse functions. With that being the case, you remember the graphs. The graphs of two functions that are inverse functions are symmetric with respect to the line y equals x. When x is between 0 and 1, that means here, the graph of y equals ln x is below the x-axis, and that's why ln x is negative. At 1 is 0, and then when x is larger than 1, different color. So that means if we are here, then the graph is above the x-axis and ln becomes positive. All right. We discussed that y equals e to the power of x crosses the y-axis with a slope of 1. The same thing happens with ln x. You don't have to worry about that. That's a calculus part we discussed. Also, I hope everybody remembers the change of base formula. Generally speaking, calculators can handle base 10 common law and base e natural law. But if the base is anything other than that, then we need to use the change of base formula. Okay, and whether we use log x over log b or ln x over ln b makes no difference. We get to the same answer. Okay, so I hope it's clear. For today, I think that would be it. Maybe there are a couple of questions that I think you can handle it on your own. It's really not a bad idea to see if you're comfortable with those. I put them there with details.